Hi, I'm Dr. Mike. Have you ever stopped to think about where your energy really comes from? Not the coffee, not the energy drink, not the sheer force of will you muster on a Monday morning. I'm talking about the fundamental biological spark of life itself. That spark, that power grid that runs everything from your thoughts to your footsteps, is generated deep within your cells. And when that power grid starts to fail, well, that's when things start to go very, very wrong. Today, we're going deep. We're journeying into the microscopic engines that power your entire existence, the mitochondria. More specifically, we're pulling back the curtain on the assembly line inside them, the electron transport chain. This is not meant to treat, diagnose, cure, and is purely for entertainment. Research peptides are not for human or veterinary use. Use extreme caution when entering the gray market and arm yourself with knowledge. So, what is this electron transport chain, or ETC? Forget the dry textbook definitions for a moment. Picture an incredibly sophisticated, microscopic power plant with a 5-stage assembly line embedded in the wall of your inner mitochondrial membrane. Its job is to take the high-energy electrons delivered by delivery trucks named NADH and FADH2 and pass them down this line like a hot potato. Each handoff releases a little bit of energy, which is used to pump protons. Think of them as tiny charged particles into a holding area. This creates an immense amount of pressure, a powerful electrochemical gradient. It's like building up water behind a massive dam. And the final step is to unleash that pressure through a magnificent molecular water wheel. This is complex 5, or ATP synthase. As the protons rush back through, it spins, and with every turn, it slaps a phosphate group onto a molecule called ADP, creating ATP, the universal energy currency of your body. This isn't just about having energy to go to the gym. ATP powers every single thing you do. Every heartbeat, every thought, every cellular repair job. Oxidative phosphorylation, the process run by the ETC, generates over 90% of your body's total energy. It is, without exaggeration, the engine of life. Let's quickly review the crew on this assembly line because knowing the players helps us understand how to fix things when they break. First up is Complex 1, the big L-shaped entry point for electrons from NADH. It's a powerhouse, pumping 4 protons for every electron pair it processes. Clinically, this is critical. Complex 1 is fussy. It requires cofactors like flavin mononucleotide, derived from vitamin B2, and iron-sulfur clusters. A deficiency here is like taking away a key worker's favorite tool. The whole line slows down. Next is Complex 2, succinate dehydrogenase. This is the alternate entry point for electrons coming from FADH2. It's a solid contributor, but it's a bit of a slacker compared to its neighbor. It doesn't pump any protons itself. It just passes the electron off. The handoff goes to our first mobile carrier, coenzyme Q, or ubiquinone. Think of it as a microscopic shuttle bus, ferrying electrons from complexes 1 and 2 over to the next big station. That station is Complex 3, cytochrome C reductase. It takes the electrons from CoQ10, gets another jolt of energy, and pumps 4 more protons across the membrane, contributing significantly to that power-generating gradient. From there, the electron hops onto our second shuttle bus, cytochrome C, which carries it to the final destination on the line. And that is Complex 4, cytochrome C oxidase. This is the grand finale. Here, the now low-energy electron is handed off to the ultimate electron acceptor, oxygen. This is the entire reason you breathe. The oxygen combines with some protons to form water, a harmless byproduct. Complex 4 is another specialist, requiring copper to function correctly. Without oxygen, or without copper, this final step backs up and the entire energy production line grinds to a catastrophic halt. So you have this beautiful linear chain of events. But here's where the science gets really, really cool and moves beyond the standard textbook diagram. It turns out these complexes don't just sit there waiting for an electron shuttle bus to arrive. Cutting-edge research reveals they organize themselves into elegant, functional megastructures called supercomplexes, or respirosomes. They literally huddle together. Why does this matter? It's all about efficiency and safety. This organization creates a phenomenon called substrate channeling. Instead of CoQ10 and cytochrome C floating around hoping to bump into the right complex, the electron is passed directly from one station to the next within the supercomplex. This has two profound clinical implications. First, it dramatically speeds up ATP production. Second, and arguably more important, it minimizes electron leakage. When an electron accidentally escapes the chain, it can react with oxygen to create a highly damaging molecule called a reactive oxygen species, or ROS. Think of ROS as molecular sparks flying off a faulty machine. A few are manageable, but a constant barrage leads to oxidative stress, which is like cellular rust. It damages everything it touches. Supercomplexes are the body's way of keeping that machine tightly sealed and running clean. And the glue that holds these supercomplexes together is a special phospholipid in the membrane called cardiolipin. Remember that name because it is a prime therapeutic target we'll be discussing later. The integrity of the respirosome is ground zero for mitochondrial health. So what happens when this exquisitely designed engine starts to fail? When the complexes become inefficient, when the supercomplexes fall apart, when the membrane becomes leaky, the consequences are not trivial. This is a central feature in aging and nearly every major chronic disease. Take neurodegeneration. The brain is an energy hog, consuming about 20% of your body's oxygen and calories, despite being only 2% of your body weight. It is therefore incredibly sensitive to any disruption in its power supply. A massive body of evidence links impaired complex 1 activity directly to the pathogenesis of Parkinson's disease. When complex 1 is inhibited, the dopaminergic neurons that control movement begin to die off. They are starved of energy and simultaneously poisoned by the resulting oxidative stress. In Alzheimer's disease, we see a similar story, but the main culprit often appears to be complex 4. Reduced activity of this final complex, coupled with accumulating damage to mitochondrial DNA, is a hallmark feature in the brains of Alzheimer's patients. This energy crisis cripples synaptic function and neuronal repair, accelerating cognitive decline. The failure of the ETC is also a key driver of metabolic syndrome. Healthy mitochondria are metabolically flexible. They can efficiently switch between burning glucose and fatty acids for fuel. In insulin resistance, this flexibility is lost. Impaired oxidative phosphorylation causes a traffic jam. Lipid intermediates build up inside the cell, literally getting in the way and interfering with insulin signaling. The cell becomes deaf to insulin's message to take up glucose, and blood sugar levels begin to rise. This same bioenergetic crisis is at the heart of heart failure. The heart is a relentless muscle. It never rests. A failing heart is quite literally an engine that has run out of fuel. It cannot generate enough ATP to meet its immense contractile demand. The research is clear. Diminished mitochondrial respiratory capacity is a powerful predictor of mortality in patients with cardiovascular and metabolic disease. Okay, that was the bad news. The good news? We can fight back. Optimizing the function of the electron transport chain isn't about one magic bullet. It requires an integrated, multi-modal approach, layering interventions from the foundational to the highly advanced. The most powerful signals you can send to your mitochondria are through lifestyle. At the top of the list is exercise. Both endurance training and high-intensity interval training, or HIIT, are fantastic. But HIIT seems to have a special magic for mitochondrial health. Intense exercise activates a master regulator of energy metabolism called PGC1 alpha. Think of PGC1 alpha as the foreman of your cellular construction crew. When activated, it shouts the order to build more mitochondria. This process, called mitochondrial biogenesis, increases the number and functional capacity of your cellular power plants. Next up is caloric restriction and fasting. Forcing your body to go for periods without energy input is a powerful stress signal, a good kind of stress. It activates pathways like autophagy, which is your cell's housekeeping service. It identifies old, dysfunctional mitochondria and recycles them for parts. Intermittent fasting or time-restricted eating, such as confining your meals to an 8-hour window each day, can provide these benefits without the challenge of long-term, severe calorie cutting. It improves metabolic flexibility and boosts overall ETC efficiency. Once the lifestyle foundation is in place, we can move on to targeted nutritional support. It's just common sense. You can't run an assembly line if you don't give the workers the raw materials they need. Coenzyme Q10 is a no-brainer. It's the literal shuttle bus carrying electrons between the first few complexes. Statin medications, taken by millions, are notorious for depleting CoQ10 levels. For optimal absorption, the ubiquinol form is generally considered superior. Another powerful compound is pyrroloquinoline quinone, or PQQ. PQQ works synergistically with CoQ10. While CoQ10 helps the existing mitochondria work better, PQQ activates that same PGC1 alpha pathway we talked about with exercise, stimulating the creation of entirely new mitochondria. We also have the basics, the B vitamins. Specifically, B2, riboflavin, is a precursor to FAD, which feeds electrons into complex 2. And B3, niacin, is a precursor to the superstar molecule NAD+, which feeds electrons into complex 1. And that brings us to NAD+, or nicotinamide adenine dinucleotide. This molecule is absolutely paramount. It's the primary electron delivery truck for complex 1. But its job doesn't stop there. It's also a critical fuel for sirtuins, a family of proteins that act as master regulators of cellular health and longevity. The tragic reality is that our cellular levels of NAD+ decline precipitously as we age, by as much as 50%. This starves the ETC of its primary substrate and cripples our cellular defense systems. This is why there's so much excitement around supplementing with NAD+ precursors like nicotinamide riboside, or NR, and nicotinamide mononucleotide, or NMN. The goal is to refill the NAD+ tank, boosting the input to the ETC and reactivating those protective sirtuins. Finally, under the pharmacological umbrella, we have to talk about metformin. Long used for type 2 diabetes, its benefits go far beyond blood sugar control. Metformin acts as a mild, transient inhibitor of complex 1. Now, why would inhibiting our energy production be a good thing? It's a clever trick. This slight inhibition momentarily reduces ATP output, which increases the cellular ratio of AMP to ATP. This rise in AMP flips a master metabolic switch called AMPK. Once activated, AMPK triggers a cascade of profoundly beneficial effects, including enhanced glucose uptake, increased fatty acid oxidation, and, you guessed it, stimulation of mitochondrial biogenesis. It's a classic example of what doesn't kill you makes you stronger on a cellular level. Foundational support is crucial, but the future of mitochondrial medicine lies in therapies that are far more precise and targeted. This is where we get into the truly cutting-edge science. And at the top of that list is a peptide called elimipritide, also known as SS31. Unlike a general antioxidant or a nutrient cofactor, elimipritide has an incredibly specific and elegant mechanism of action. This small, water-soluble tetrapeptide is designed to travel directly to the inner mitochondrial membrane, where it seeks out and binds to that special phospholipid we mentioned earlier, cardiolipin. Remember, cardiolipin is the structural glue that anchors the ETC complexes and helps organize them into those hyper-efficient respirasomes. In aging and disease, cardiolipin is a prime target for oxidative damage. As it degrades, the supercomplexes destabilize and fall apart. This is catastrophic. It leads to massive electron leakage, a firestorm of ROS production, and a dramatic collapse in ATP output. It's a vicious cycle of energy failure and oxidative damage. Elimipritide's genius is that it intervenes at the source of the problem. By binding to cardiolipin, it shields it from oxidative damage and helps restore the structural integrity of the inner membrane. This allows the functional respirasomes to reassemble. The effects are profound. Electron flow becomes more efficient, pathological ROS production plummets because the leaks are plugged, and ATP synthesis is restored. It's not just supporting the ETC with raw materials, it's actively repairing the structural foundation of the engine itself. Now, it's important to note that elimipritide, or SS31, is still an investigational drug. While it has shown incredible promise in clinical trials for conditions like Barth syndrome and primary mitochondrial myopathy, it is not yet widely available except in research settings. But it represents a paradigm shift in how we approach mitochondrial medicine. Other novel therapies are also emerging. Agents like Mitoq, for example, use a clever chemical trick. They attach the antioxidant CoQ10 to a molecule called a triphenylphosphonium cation, which acts like a GPS tracker, guiding the CoQ10 to concentrate specifically inside the mitochondria. This strategy of creating targeted antioxidants is powerful, but many experts believe the real future lies in therapies like elamoprotide that restore the underlying structural integrity, preventing the fire from starting in the first place, rather than just trying to put it out. So how do we put all this information into practice? A responsible clinical approach moves from broad assessment to a tiered, personalized intervention strategy. Step 1 is advanced functional testing. We need to look beyond standard blood work. A urine organic acids test, or OAT, is one of the most valuable tools for assessing mitochondrial health. It's like looking at the exhaust fumes from your cellular engines. Elevated levels of intermediates from the Krebs cycle, the process that generates NADH and FADH2, can indicate specific bottlenecks or cofactor deficiencies. High lactate or pyruvate can suggest that energy substrates aren't even making it into the mitochondria properly. It's also critical to assess intracellular nutrient levels. Looking at levels of minerals like magnesium and copper or CoQ10 inside the red blood cells gives a much more accurate picture of what's available to the mitochondria than standard serum levels, which just show what's floating around in the blood. And for an even deeper dive, advanced markers are becoming more accessible. Measuring plasma NAD+ levels, a marker of oxidative DNA damage called 8-hydroxy-2'-deoxyguanosine, or cell-free mitochondrial DNA, can give us a direct window into the level of mitochondrial stress and turnover. Step 2 is the tiered intervention. Based on the patient's clinical picture and lab results, we structure the protocol to ensure we're not trying to build a roof before the foundation is poured. Tier 1 is foundational support. This is for absolutely everyone. It consists of lifestyle modifications, the right diet, consistent exercise, and quality sleep, along with ensuring core nutritional needs are met with things like a good multivitamin, magnesium, and a B complex. This is the non-negotiable bedrock. Tier 2 is targeted nutraceuticals. This is for patients with specific needs based on their age, lifestyle, or biomarker data. This is where we bring in therapeutic doses of CoQ10, PQQ, and the NAD+ precursors like NMN or NR. Dosages are tailored to the individual. And Tier 3 is for advanced and pharmacological support. These interventions are reserved for specific clinical conditions like diagnosed metabolic syndrome or neurodegenerative disorders and require close clinical supervision. This is where agents like metformin or emerging therapies like mitochondrial targeted peptides would be considered. Now, this is a complex topic and it often brings up some common questions. Let's tackle a few of them. A frequent one is, what's the difference between mitochondrial support and just taking antioxidants? It's a crucial distinction. Systemic antioxidant therapy is like having a fire extinguisher. It can help put out the fires of oxidative stress. But mitochondrial support is like having a master mechanic. It fixes the faulty engine that's causing the fire in the first place. Quenching downstream ROS without addressing the root cause, the inefficient and leaky ETC, is a losing battle. The most effective long-term strategy is always to reduce ROS production at its source. Another question, what's the best way to test for NAD+ levels? While direct intracellular NAD+ testing is becoming more available, it's not yet a standard, accessible tool. In a clinical setting, the most reliable and practical method is still that indirect functional assessment. A comprehensive urine organic acids test remains the single best window into the real-world function of your energy pathways. What about safety? Are there contraindications for high doses of CoQ10 or NMN? Both are generally considered very safe. High-dose CoQ10 can occasionally cause mild GI upset. For NAD+ precursors, the main consideration is still theoretical. Because they support robust cellular growth and metabolism, subcutaneous injection of NAD+ is the preferred method over NMN. The optimization of the mitochondrial electron transport chain is no longer some theoretical pursuit for biochemists. It represents one of the most powerful and tangible clinical strategies we have for promoting healthy aging and managing chronic disease. By embracing a multi-modal, tiered framework, we can move beyond treating symptoms and address the root cause of cellular dysfunction. We can profoundly impact patient outcomes by restoring energy at the most fundamental level. The future of medicine is happening right now, deep inside the mitochondrion. It is the upstream origin of our vitality, the point where everything we do, how we move, what we eat, the therapies we choose, all converges. Mastering this domain is absolutely essential for anyone serious about longevity and root cause resolution. It's about shifting our focus from the branches of disease to the very root of cellular health. If you found this deep dive into your cellular engines valuable and you want to keep exploring the cutting edge of health science, do me a huge favor and hit that like button. It really helps the channel. And of course, make sure you subscribe and turn on notifications so you don't miss our next video where we continue to unravel the complexities of human biology. Finally, to get even more in-depth protocols, articles, and updates delivered straight to your inbox, be sure to sign up for our newsletter. The link is right where you'd expect it to be, in the description below. Thanks for watching. Stay curious, and I'll see you in the next one.